Toshiba Electronic Devices and Storage Corporation. E-learning. Basic knowledge of discrete semiconductor device. Chapter 3. Transistors. This video explains the types of transistors and their characteristics. Types of transistors. Transistors are roughly classified into three types: bipolar, field effect and insulated gate bipolar. Bipolar transistors are current-driven devices. Field effect transistors, FET, and insulated gate bipolar transistors, Igbt, are voltage-driven devices. Bipolar transistors. There are two types of bipolar transistors, NPN type and PNP type. NPN type products have low withstand voltage to high withstand voltage. PNP type products with withstand voltage of 400 volt or less, and particularly those with withstand voltage of 200 volt or less, are mainstream. There is an amplification function to convert small signals to large signals. The ratio of collector current IC and base current IB is called DC current gain, denoted as HFE. When small current, IB, flows from base to emitter, current of IB times HFE flows from collector to emitter. Bjts are current-driven devices driven by base current. Operation of NPN transistor. Base current, current from base to emitter. Collector current, current from collector to emitter. Operation of PNP transistor. Base current, current from emitter to base. Collector current, current from emitter to collector. Bias resistor built-in transistors, BRTs. BRTs are bias resistor built-in transistors. Bjts are often used together with resistors in electronic equipment. The mounting area can be reduced by using BRTs, which integrate a transistor and a resistor. Junction field effect transistors. Operation of Jfets. Jfet, junction field effect transistor. 1. In the N-channel junction field effect transistor, figure 3-3a, when a voltage is applied between the drain and the source, electrons flow from the source to the drain. 2. When a reverse bias is applied between the gate and source, the depletion layer expands and suppresses the electron flow in 1. 3. If the reverse bias voltage between the gate and source is further increased, the depletion layer blocks the channel and the flow of electrons stops. As shown above, voltage applied between gate and source controls the condition between drain and source. So FETs are voltage-driven devices. Metal oxide semiconductor field effect transistors, MOSFETs. The metal oxide semiconductor field effect transistor, MOSFET, is currently attracting the most attention among transistors. There are two types of MOSFET, N-channel and P-channel. N-channel is widely used for AC-DC power supplies, DC-DC converters, inverter equipment, etc., whereas P-channel is used for load switches, high-side switches, etc. The differences between the bipolar transistor and the MOSFET are shown in Table 3-1. Differences between Bjt and Mosfet. Explanation of the differences between on-off operation of Bjt and Mosfet. 1. Base current of BET starts flowing when base voltage increases, and collector current is in proportion to this base current. This flow starts at about 0.7 volt. This voltage is called the base emitter threshold voltage, VB. In order to make collector current flow, it is necessary to supply the base current and continuous driving power is required. 2. Since the MOSFET forms a channel according to the gate source voltage, this voltage must be a certain voltage or more. Once the channel is formed, the on state continues and the drain current continues to flow, and so the power required for the driving is small. By discharging the charge accumulated in the gate and removing the channel, it shifts to the off state. Structure and operation of MOSFET. Here we explain the operation of the MOSFET, referring to figure 3-6a. 1. Apply voltage between drain and source with positive drain polarity. Drain source voltage, VDS. 2. Apply voltage between gate and source with positive gate polarity. Gate source voltage, VGS. 3. As a result, electrons are attracted to the p-type layer just under the gate insulator film, and part of the p-type layer is turned into n-type region. This n-type region in this p-type layer is called the inversion layer, channel. 4. As this inversion layer is completed, an N layer path is formed from the drain to the source of the MOSFET. N plus, N minus, inversion layer, N plus 5. As a result, the MOSFET works at low resistance, and drain current is determined by applied VDS and load flows. MOSFET performance improvement, decision factors of RDS, UN. 1. The MOSFET device structure is selected according to the required voltage rating, VDSS. For example, many middle and high voltage MOSFETs, VDSS equal 250 volt or higher, have planar gate MOS, poly MOS, structure, and products with less than VDSS equal 200 volt have more trench gate MOS, UMOS. 2. The factor that determine the on resistance RDS, UN, are shown in figure 3-7 and equation 3-1. Depending on the structure and VDSS of MOSFET, the ratio of factors determining RDS, UN, will change. When the poly MOS structure is chosen, R drift becomes the dominant factor in VDSS equals 600 volt products, while the ratio of RCH plus RJFET is high in VDSS equal 30 volt products. However, by applying new MOS structure, RCH will be very small. MOSFET performance improvement, approach to low RDS, UN. We are pursuing the following countermeasures for the biggest problem of MOSFET: how to effectively reduce on resistance by effectively utilizing the element area. 1. High voltage, reduce resistance of drift by the advanced superjunction process explained on the next page. 2. Low voltage, minimize resistance of RCH by fine patterning of trench structure and reduce resistance of RSUB by thinning wafer. MOSFET performance improvement, superjunction MOSFETs. SJ-MOS. 1. SJ-MOS has pillar-shaped P layer, P pillar layer, in N layer. P and N layers are aligned alternately. 2. Depletion layer spreads an N layer by applying VDS, but the way it spreads in SJ-MOS is different from the case of general DMOS. 3. In the case of DMOS, the electric field intensity is the strongest at P and N layer interface. When the electric field intensity exceeds the limit of silicon, breakover breakdown phenomenon, occurs, and this is the voltage limit. On the other hand, in the case of SJ-MOS, the electric field intensity is uniform in N layer. 4. As a result, SJ-MOS can be designed with N layer that has lower resistance, realizing low on resistance products. SJ-MOS can realize lower on resistance with the same size chip as DMOS. Summary of MOSFET features by structure. Features and main applications based on the structure of various MOSFETs are shown in Table 3-2. Withstand voltage, the optimum structure is selected for the target withstand voltage. Low on resistance, UMOS for products with 250 volt or less, SJ-MOS or DT-MOS, are advantageous for products with more than that. High current, the same tendency as for low on resistance. High speed, UMOS is disadvantageous for high-speed switching because of large gate capacity, CISS. Depending on the product, it is also commercialized for high-speed switching designed for small, R-on-time CISS by taking advantage of the low on resistance characteristic. Performance of MOSFETs, drain current and power dissipation. Permissible loss and drain current, which are typical maximum ratings of MOSFET, are calculated as follows. Power dissipation is calculated by thermal resistance and channel temperature. Drain current is calculated by the calculated power dissipation and on resistance, using Ohm's law. Performance of MOSFETs, avalanche capability. As a feature of MOSFET, if it is within a certain energy, drain current ID and below the rated channel temperature T channel, there is performance that does not break even if it exceeds the rated voltage VDSS. This is called avalanche capability, the allowable energy is called avalanche energy, and the current is called avalanche current. Performance of MOSFETs, characteristic of capacitance. Capacitance characteristics of CISS, CRSS and COSS are important factors affecting switching characteristics of MOSFET. CISS, input capacitance. Sum of gate drain and gate source capacitance, it influences delay time, the bigger the CISS, the longer the delay time. CRSS, reverse transfer capacitance. Gate drain capacitance, the bigger the CRSS, the more the characteristic of drain current rising deteriorates, which is disadvantageous for MOSFET's loss. Low capacitance is needed to drive at high speed. COSS output capacitance. Sum of gate drain and drain source capacitance, it influences turnoff characteristic and loss with light load. In the case of large COSS, turnoff dVdt decreases, which is advantageous for noise. But loss with light load increases. Performance of MOSFETs, safe operating area. There are two modes of safe operating area. 1. Forward bias SOA, FBSOA. Usable area of current and voltage at on status. 2. Reverse bias SOA, RBSOA. Usable area of current and voltage at turn-off operation. Applied pulse width is very narrow because of use under switching operation. Each mode can be defined as shown in figure 3-12a. As for the guarantee of avalanche, rated voltage and current operation, short time, at turn-off is generally guaranteed as for the MOSFET, but RBSOA has not been announced. FBSOA consists of three restriction areas, rated current, rated voltage and thermal resistance areas, and secondary breakdown area. The three restriction areas are limited by ratings of device or calculated from thermal resistance. But secondary breakdown area is obtained by measurement of the actual device. Insulated gate bipolar transistors, IGBTs. An IGBT is a device suitable for high current control combining a voltage-driven MOSFET in the front stage and a transistor allowing a large current to flow in the rear stage. Equivalent circuit and operation details. The equivalent circuit of the IGBT is shown in figure 3-13b. The RBE value is set so that the NPN transistor does not turn on. Applying on signal to gate of an N-channel MOSFET turns on conduction state. As a result, current flows from the emitter to the base of PNP transistor. This base current works to lower the on resistance of N-channel MOSFET. Comparison with MOSFET. Gate driving operation is the same as N-channel MOSFETs. In on-state, decrement of on resistance of N-channel MOS enables high current flow. Voltage drop across the emitter and base of PNP transistor occurs in the entire current region. Operation of insulated gate bipolar transistors. Operation of the IGBT connected as in figure 3-14a is shown below. 1. Inversion layer is made in P layer under gate by applying positive voltage to gate. The N-channel MOSFET in figure 3-14b turns on like a normal N-channel MOSFET. 2. When the N-channel MOSFET is on status, collector's potential is positive. So, holes are injected from P+ through N+ to N-, and this injection accelerates injection of electrons from emitter. 3. As a result, increment of carriers, electrons and holes, decreases resistance of N layer that normally has higher resistance, conductivity modulation effect. Thus, on resistance of the N-channel MOSFET varies to lower as shown in figure 3-14b. Performance improvement of IGBTs, evolution of vertical design. As shown in figure 3-15a, the vertical design of the IGBT has been evolving. Starting from the PT structure, thin PT, generally called field stop, structure is becoming mainstream as thin wafers are now used. Gate structure is the same as MOSFET. What are RC IGBTs and IGTs? Reverse conductive IGBT, RC IGBT. The structure of the RC IGBT is shown in figure 3-16a. A diode is formed by making a part of the P-type layer, which is the collector of the IGBT, N-type. This diode has the same function as FWD, which is generally inserted in the IGBT. With the introduction of thin wafer technology, it became possible to commercialize this configuration. Since the diode and the IGBT are one chip, it is easy to assemble. Because it is difficult to control the performance of the diode and the IGBT separately, the RC IGBT is unsuitable for certain applications. Injection enhanced gate transistor, IGT. Generally, in the high voltage IGBT, it is difficult to obtain low VCE, SAT, characteristics because the carrier concentration of the drift layer, N-type layer, on the emitter side is low. The IGT was developed to obtain low VCE, SAT, performance at high withstand voltage, generally 1200 volt or higher. Figure 3-16b shows the IGT structure and principle. It has a trench gate structure. Drawing out of the gate electrode is thinned out. As a result, carriers are accumulated just under the thin gate electrode, increasing the carrier concentration on the emitter side. This high carrier density decreases resistance of drift layer, and makes VCE, SAT, low. Application of IGBTs. IGBTs are suitable for applications that have easy driving circuit and need high current. They are currently used in IH equipment adopting soft switching under 50 kHz, home appliances, vehicles, and a wide variety of AC drives. In future, their application fields are expected to expand to include various AC drives. Comparison of forward characteristics of IGBTs and Mosfets. This page compares the forward characteristics of the Mosfet, DMOS, and the IGT at voltage from 500 to 600 volt. In the low current area, the Mosfet has small voltage drop, and has an advantage. On the other hand, the forward voltage characteristic of the IGBT is better than that of the Mosfet in the high current area, as shown in figure 3-17. As the forward characteristic of the Mosfet has strong positive dependence on temperature, the difference in performance of IGBT and Mosfet widens as temperature increases. Comparison of transistors by structure. This table shows the difference between bipolar transistors, Mosfet and IGBT. Datasheets of Mosfet maximum ratings. This table summarizes the absolute maximum ratings. For example, drain source voltage, gate source voltage and drain current are included. Datasheets of Mosfet electrical characteristics. First table provides thermal characteristics used to calculate channel temperature. Second table summarizes the electrical characteristics of the Mosfet. For example, gate threshold voltage is included. Datasheets of Mosfet, capacitance and switching characteristics. This page summarizes the capacitance and switching characteristics of Mosfet. For example, gate drain and gate source capacitance and rise time, DR, are included. Datasheets of Mosfet, body diode. This table summarizes the electrical characteristics of body diodes. For example, drain reverse current and reverse recovery time are included.